We have a habit of thinking in terms of off and on. A light switch is either passing current or it isn't. A heart is either beating or it is still. We extend this logic to the universe itself. We assume that if you take a field, the electromagnetic field, for instance, and you remove every photon, every bit of light, and every radio wave, that the field simply clicks off. You assume it drops to zero. This is your first mistake. In the world of the very small, zero is a physical impossibility. To understand why, you have to stop thinking of the vacuum as a container and start thinking of it as a collection of springs. Imagine every point in space is occupied by a tiny, invisible pendulum. In a classical world, you could stop that pendulum. You could hold it perfectly still at its lowest point. Its position would be exactly at the center, and its velocity would be exactly zero. But the universe does not allow this. There is a rule, the uncertainty principle, that acts as a floor for how quiet things can get. It states that you can never know both where a particle is and how fast it is moving with perfect precision. If you tried to force that pendulum to sit perfectly still at zero, you are claiming to know exactly where it is and exactly how fast it is moving. The universe rebels against this. As you try to pin the pendulum down, it begins to twitch. The more you try to calm it, the more violently it vibrates. It refuses to be off. This means that even in the deepest, coldest reaches of intergalactic space, the fields that make up our world are not still. They are shivering. They possess a zero-point energy. If you were to look at the vacuum through a powerful enough microscope, you wouldn't see a flat, black void. You would see a frantic, restless sea of activity. It is a constant, low-level hum that never stops. It is the static on a television screen that stays there even when the station goes off the air. You think of the vacuum as the absence of everything. In reality, the vacuum is the state of minimum energy, but in quantum mechanics, minimum does not mean nothing. It means the lowest possible jitter. This jitter isn't a flaw in our measurements. It isn't a ghost in the machine. It is the machine. Every cubic centimeter of what you call empty space is packed with this restless, unyielding motion. And while a little bit of shivering might seem harmless, when you add up all those little twitches across the entire universe, you find yourself staring into a mathematical abyss. If the jitter of a single quantum pendulum is small, you might think the total energy of the vacuum is similarly negligible. But physics doesn't stop at one pendulum. In quantum field theory, space is not made of discrete points. It is a continuous fabric. To calculate the total energy of the vacuum, we have to account for every possible way that fabric can vibrate. Think of a guitar string. It can vibrate at a fundamental frequency, one long, low note, but it can also vibrate in halves, thirds, quarters, and so on, creating a ladder of higher and higher pitches, or harmonics. The vacuum is like a guitar string that can vibrate at every frequency imaginable. And according to the rules we established, every single one of those frequencies must have its own zero-point energy, even the smallest, most frantic vibrations, the ones with wavelengths shorter than an atom, shorter than a nucleus, contribute their own shiver of energy to the total. When you sit down to do the math, you begin to add them up. You add the energy of the long waves, then the medium waves, then the short waves. You keep adding, and the sum keeps growing. In a sensible world, these higher frequencies would eventually lose steam and fade away. But they don't. The math is relentless. As you move toward infinitely small wavelengths, the energy of each vibration doesn't disappear. It actually increases. You are summing a list of numbers that never gets smaller. $1 plus 2 plus 3 plus 4. The result is not a large number. It is not a massive number. It is infinity. This is the vacuum catastrophe, our best equations, the ones that describe the behavior of electrons and light with staggering precision, tell us that every empty coffee cup, every inch of your bedroom, and every void between the stars contains an infinite amount of energy density. If this were literally true in the way you experience the world, the universe would have ended before it began. Infinite energy means infinite weight. Infinite weight means infinite gravity. The entire cosmos should have curled into a ball smaller than a grain of sand the moment it was born. Yet, here you are. You are breathing. You are walking through this infinite energy as if it were nothing at all. You feel no weight. You feel no heat. This creates a profound tension. Either the math is a total hallucination, or the nothingness you see is actually a mask for a reality so dense it defies your ability to perceive it. We are forced to ask, how can something be infinite and yet, for all practical purposes, invisible? When a physicist encounters infinity in an equation, it is usually a sign that they have made a mistake. It is nature's way of saying, you've pushed the logic too far. But with the vacuum, the infinity wouldn't go away. It was baked into the very crust of the theory. So, we did something that sounds like cheating. We decided to ignore it. We developed a technique called renormalization. The logic is deceptively simple, since we cannot see this infinite background energy, and since it doesn't seem to affect our daily lives, we will simply declare it to be our new zero. Imagine you are standing on a plateau that is 10,000 feet above sea level. If you want to build a house, you don't care that the ground is 10,000 feet up. You only care how high the walls are relative to the floor. You redefine the plateau as zero height. You subtract the 10,000 feet from every calculation you make. In physics, we do the same with the vacuum. We say that the absolute energy doesn't matter. What matters is the change in energy. When an electron jumps from one state to another, it releases a photon. We measure that photon. We measure the ripple on the surface of the pond, while blissfully ignoring the fact that the pond is infinitely deep. Richard Feynman was famously uneasy with this. He called it hocus pocus and dippy process. It felt like sweeping the most important fact about the universe under a rug because the math was too embarrassing to look at. But it worked. By subtracting the infinity, by treating the vacuum as a blank slate despite knowing it was full, we were able to predict the behavior of particles with a precision equivalent to measuring the distance from New York to Los Angeles within the width of a human hair. This success created a dangerous comfort. It allowed us to go back to believing the vacuum was empty. We convinced ourselves that the zero-point energy was just a mathematical ghost, a bookkeeping error that we had successfully corrected. We told ourselves that the background noise of the universe didn't actually exist in a physical sense because it didn't push on anything. We were wrong. It does push. And in 1948, we found a way to catch it in the act. In 1948, a Dutch physicist named Hendrik Casimir proposed a thought experiment that turned the mathematical ghost of the vacuum into a physical sledgehammer. He imagined taking two uncharged metal plates and placing them incredibly close together in a perfect vacuum. In your intuitive world, nothing should happen. The plates have no electric charge. There is no air to push them. There is nothing between them but nothing. But if the vacuum is actually a sea of fluctuations, a collection of every possible frequency, then the plates change the math. Think of the space between the plates like a small organ pipe. Only certain notes can play inside that pipe, the ones whose wavelengths fit perfectly within its walls. The long, low-frequency waves are simply too big to exist in that tiny gap. They are excluded. Outside the plates, however, the vacuum is unrestricted. Every frequency, from the long to the infinitely short, is present and pushing. Because there are more modes of vibration pushing from the outside than there are from the inside, a net force is created. The nothing on the outside pushes harder than the nothing on the inside. The plates are slammed together. This isn't a theory. It has been measured in laboratories. We have seen the vacuum exert real, mechanical pressure on physical objects. It is called the Casimir Effect, and it is the moment our renormalization trick begins to fail us. It proves that the energy we tried to subtract away is physically present. It has consequences, and it's not just the Casimir Effect. We see it in the lamp shift, where the energy levels of an atom are slightly nudged because the electron is constantly being buffeted by these vacuum fluctuations. The electron is like a boat on a choppy sea. Even when the wind is dead, the waves keep it bobbing. This forces a terrifying realization. The reason we don't feel the infinite energy of the vacuum isn't that it's not there, it's that it is everywhere. It is perfectly uniform. It pushes on you from the left with the same infinite force it pushes from the right. You are like a deep-sea fish that doesn't realize it is under thousands of pounds of water pressure because that pressure is inside its lungs, its blood, and its cells. You only notice the vacuum when you find a way to get a little bit of it out of the way. But as long as we stay in our plateau, we can pretend the ocean doesn't exist until we look at the sky. The trick of subtraction works perfectly as long as you are playing with atoms and light. In the small-scale world of quantum mechanics, you can ignore the floor because you only care about how high you jump. But there is one force in the universe that is not fooled by our accounting tricks. Gravity. Gravity is the ultimate auditor. It does not care about differences or relative changes. According to Einstein's general relativity, gravity reacts to the total energy density of a space. It weighs everything. If the vacuum has energy, even the invisible zero-point energy we tried to subtract away, then that energy must have weight. It must exert a gravitational pull. When we use our quantum equations to calculate how much weight the vacuum should have, we get a number. When we look at the universe through our telescopes to see how much Weight is actually there by measuring how fast the universe is expanding. We get another number. The discrepancy is not small. The quantum calculation predicts vacuum energy density that is $10,120 times larger than what we observe. That is a 1 followed by 120 zeros. To give you a sense of how catastrophic this is, if you are off by this much when measuring the width of the entire observable universe, your error would be smaller than the diameter of a single atomic nucleus. This is the greatest failure in the history of theoretical physics. It is the moment where our two most successful ways of describing reality, quantum mechanics, and general relativity crash into each other and shatter. One theory says the vacuum should be so heavy it would crush the universe into a point instantly. The other says the vacuum is so light it barely nudges the expansion of the galaxies. We are missing something fundamental. Some physicists suggest that there is a cancellation we haven't discovered yet, that for every bit of positive energy in the vacuum, there is a hidden piece of negative energy that cancels it out to nearly zero. But this cancellation would have to be accurate to 120 decimal places. It would be the most precise accident in the history of existence. You are currently standing in the middle of this disaster. Your body, your home, and your planet exist only because this infinite energy is somehow, miraculously, being suppressed. You are living on the razor's edge of a mathematical impossibility. We have spent centuries thinking of ourselves as the solid things in a hollow world. We think of atoms as the stuff and the vacuum as the gap between the stuff. But we have it backward. The vacuum is the only thing that is truly solid. It is the dense, high-energy foundation of everything. What you call matter, the electrons in your skin, the protons in your bones are not separate entities living on the vacuum. They are ripples of the vacuum. Imagine a massive, turbulent ocean. You see a whitecap, a bit of foam tossed up by a wave. You point at the foam and call it me. You point at the vast, dark, unfathomable depths beneath it and call it nothing. But the foam is just a temporary, low-energy configuration of the ocean itself. Without the water, there is no foam. Without the vacuum, there is no you. This shifts the nature of our existence from the substantial to the accidental. We are not the protagonists of reality. We are the leftovers. We are the tiny, fractional remainder of a cosmic subtraction that almost, but not quite, reached zero. We are the static that survived. When Richard Feynman looked at the vacuum, he didn't see a void. He saw a playground of infinite potential where particles are constantly winking in and out of existence, borrowing energy from the nothingness and then paying it back a billionth of a second later. He saw a universe that is never truly quiet, never truly empty, and never truly still. We still do not know why the infinite energy of the vacuum hasn't swallowed us whole. We do not know why the cancellation is so perfect, or what secret law of nature keeps the nothing from exploding. We are like ants living on the surface of a dormant volcano, unaware that the ground beneath us is a reservoir of power that defies calculation. You are not a solid object moving through a void. You are a ghost, a shimmering disturbance in an infinite sea of energy. You are what happens when nothing gets excited. In the end, the vacuum isn't the absence of everything. It is the presence of everything else. And the more we try to empty the box, the more we realize that the box was the most interesting thing all along. There is a final, humbling realization waiting at the bottom of the vacuum. If you were to succeed in your original mission, if you could somehow truly empty space, silencing every jitter and canceling every field, the universe as we know it would cease to exist. Time itself would lose its meaning. Without the restless fluctuations of the vacuum, there would be no mass. Without mass, there is no gravity. Without gravity, there is no geometry to the cosmos. We often find comfort in the idea of nothing. We find it peaceful. But a true vacuum, a literal, mathematical zero, would be the ultimate heat death. It would be a silence so profound that not even a single thought could echo within it. We exist only because the universe is loud. We exist in the noise. When you look up at the night sky, at the vast black gaps between the stars, do not feel small because of the emptiness. Feel small because of the fullness. You are looking at a reservoir of energy so vast that a single cubic meter of it could, in theory, boil all the oceans on Earth in an instant. We are the beneficiaries of a cosmic tension. We are balanced between an infinite presence and an impossible absence. We are the survivors of a war between two infinities that almost perfectly destroyed one another. Richard Feynman once said that nature has a great simplicity and therefore a great beauty, but the vacuum teaches us that this beauty is a mask. Beneath the simple, quiet appearance of nothing lies a complexity so violent and a density so extreme that our language for reality begins to fail. The next time you look at a shadow, or the dark space in a room, remember that you aren't looking at a lack of something. You are looking at the surface of an infinite ocean, disguised as a void. You are not the observer of the universe. You are the universe observing its own restless, shimmering self.